Hi, my name is Kristen Rollins, and today I'll be going through a time series analysis of some London bike sharing data. First, let's get familiar with the bike sharing system. So this was developed in 2008 to reduce traffic congestion in London. How it works is that you can grab a bike from a docking station around the city, ride it to your destination, and then return it to any other docking station nearby. And this is nice because there's lots of these stations and bikes around the city. Plus, it doesn't cost much, so this is a neat idea and a good deal if you're able and willing to ride a bike every so often. The data that we're working with spans 2 years, 2015 and 16. The main variable we're going to look at is count, which is just the number of bikes that were newly rented in a certain time period. There are other variables collected as well, mostly dealing with the weather. So we have temperature, the feels like temperature, the percent humidity, wind speed, and weather code, which is just a scale from 1 to 100 where it ranges from a totally clear day all the way to freezing fog. It also records whether it's a holiday, whether it's a weekend, and what season it's in. These 4 in bold here are ones that I'll be including in some of my models later, since they seem to capture the most information without being redundant. I also want to note that the original data was hourly, but I summed the values and converted it to daily data, which I think is easier to visualize and wrestle with. With this analysis, stakeholders of the bike sharing program can determine how effective the initiative was and also decide if they need to put more bikes out into the city. I will also be making forecasts so they can see whether the cycling popularity seems to be rising or declining, and based on the forecast, they can also estimate the profits they'll be making from those bicycle rentals. So I want to start with a univariate analysis where we're only looking at our target variable of bicycle counts. Here's the original data, the sample autocorrelations, and spectral densities. First, I want to make sure we know this is non-stationary data, as it definitely violates the first condition of constant mean. If we were to roll back the clock and observe all of this again, I'd expect very similar values to happen, where there's more riders during the week and also during the summer. So the numbers definitely depend on where they are in the time series. So I suspect both yearly and weekly seasonality because we can see in this more granular spectral density plot that the 1/365 frequency is present, as well as a 1/7 frequency. We also have higher autocorrelations at 7, 14, and 21. So this is the process that I went through. First, I identified this 365 seasonal factor just by observation, since we can't really make an overfit table to confirm this. But after transforming the data by this factor, this is what we're left with. And we can now make an overfit table to see if a weekly seasonal factor is present. And there is some evidence for this, but it's not a super strong match, but it's strong enough for me to move forward with this extra seasonal or weekly factor. So this is what I was left with, which I then fit with an AR8. So this is my final ARUMA model, which gets an ASE of almost 32 million over the last 60 days, or 2 months, which we can use to compare with other models. Next, I want to do a multivariate analysis to try to leverage the extra information to get better forecasts. I first made a multiple linear regression model with correlated errors. In this model, I found that all of the variables were significant. So temperature had a strong positive coefficient, weather code had a strong negative coefficient, holiday had a fairly strong negative, and weekend had another strong negative coefficient. And it got an ASE a little worse than the previous one, but it still follows pretty well. I really like this model because it gets at our intuition that if it's a nice sunny day, then people will ride the bikes. But if it's snowing and cold, then no, they're not going to ride them. But there is at least a simple autoregressive process that's still present. So if someone rides a bike one day, maybe they're more likely to ride it the next day as well because they enjoyed it. So even though this doesn't perform quite as well as the ARUMA model before, I think it's a very useful one. Next, I tried a vector autoregressive model, which is a generalization of an AR model that can incorporate multiple variables. I used the same variables as before and selected a VAR with lag 7 model based on the AIC criteria. This turned out to get a really bad ASE. This is because it assumes that all the variables are stationary, which is definitely not the case as we talked about before. So the forecasted behavior is cyclic and tries to return to the mean, but this is not really appropriate for our data. So this is a good try, but we'll move on. Next, I tried a neural network. This is a multi-layered perceptron, which has 9 inputs for various lags of all the variables, as well as 5 hidden nodes, and then 1 output, which is the forecast. This gets an ASE pretty close to ones we had before, which is a good sign because this was run with mostly default parameters. So with more parameter tuning and trying out new network structures, I think this one is promising. Finally, I created an ensemble model that combines the forecast for my 2 best models so far, which were the ARUMA and MLR with correlated errors. I took the average of the 2 forecasts at each time point, and it turned out really well, with the best ASE so far for forecasting these last 60 days. So this is neat that it's able to leverage the strengths of both models and perform even better. So comparing the 5 models I created, we see that the ensemble model did have the best ASE, but it's important to note that those were based on true values of the explanatory variables. This would be good for maybe a short-term forecast where we're confident in the weather forecast for the next week or so. But for longer-term forecasts, I would choose the ARUMA model, which is univariate, so we don't have to depend on long-term forecasts of other variables. Since the stakeholders are interested in the overall popularity of the program, here are my forecasts for a whole year out using the ARUMA model. And here are the prediction limits as well. Because the model has a couple of 1 - b factors folded into these seasonal components, those limits go pretty far out and maybe aren't super useful, but it shows that it could trend up or down based on the trend from previous years. But this model indicates that the next year will follow the previous years pretty closely, which is valuable information for the stakeholders of the London Bike Sharing Program. I hope this was informative, and thank you.